So good morning, everybody, and welcome to my last lecture. So this morning I have written something. Let me see if yeah. I don't know why. Oh, okay. So this morning I will first conclude my this sort of lecture on entropy, which started last Wednesday, with some comments on what we have found and an example which was inspired by a question posed by one of you, I think you, about the relation between the Landau frame and this general frame, which in a sense this example that I'm going to show, discuss, is has the purpose of showing that the thermodynamics is less trivial than one may naively think. So what we found last Wednesday was that one can write down an expression of entropy, which is the sum entropy current, okay, from which one calculate total entropy. So remind you that this is the basic relation. And what now I want to focus on is this hypersurface. So the hypersurface which is chosen to express entropy is very important. And one may wonder whether this entropy current is really an independent field. So that means, is it a field which is independent of the choice of a foliation, so of a family of hypersurfaces, or is it dependent? That's a very important question. And the answer is, apparently, so you may see here that it involves three terms. Okay, you may have an arbitrary number of terms if you have more conserved currents here, but assume that you have one current. You can see that you have objective fields, and I mean objective fields are J mu and T mu nu. They are objective in that they are the mean value of an operator. Okay, so that is, which is defined at any point x. So they are objective. Then you have this phi mu, which is an integral, and you may show that this integral can be expressed as a function of these objective fields. Therefore, this is most likely objective. But certainly, beta nu and zeta, they are not, because they depend on the hypersurface which has been chosen to enforce the constraint. Therefore, this expression does not seem to be, is not independent of the foliation. Okay? This is an important remark. So what does it mean? Well, it means that it may, well, first of all, that the entropy current, somehow depends on the choice of a family of hypersurfaces, so geometric dependent. This may sound surprising. And in classical thermodynamics, for instance, this is totally negligible because there is one hypersurface which is usually chosen, which is the Euclidean space, which is absolute. Okay, so therefore, entropy current in the non-relativistic limit is objective, but in the relativistic framework it is not. It may be made objective only if the foliation is chosen, is fixed. So if you choose a foliation for which is physical in some respect. An example is to choose the hypersurface which are orthogonal to beta itself. So this is a sort of self-consistent choice, such that the family of hypersurfaces is orthogonal to beta. This is possible only if beta is non-vorticus field, And in a general case of vorticals, for instance, we have rotation, this is not possible. Therefore, this choice should be changed in this case, and well, this is an open issue, I would say. So how to make this entropy current some, independent field which is not dependent on the family of hypersurface, or with a special, if there is a privilege, say, frame which makes this entropy current an objective field. The second point I want to make is the fact, as I mentioned at the beginning of this course, that this relation is not frame independent, although in most textbooks this is not even mentioned. So Ts plus mu nu equal rho plus p, as I showed at the beginning, was a key equation to obtain the constitutive equations of relativistic hydrodynamics. But this is, since this is obtained by contracting with a velocity vector the entropy current, one expects that this is not frame independent. And indeed, I want to show you an example where this non-independence is manifest. And let's go to a very simple case, which is global equilibrium. At global equilibrium, beta is objective, is a Killing vector, entropy current is unique. The reason is that when you are at global equilibrium, as we have seen, there is independence of the hypersurface. So it means that this entropy is the same whatever a sigma is. The divergence of S mu is 0. The divergence of phi mu is 0, simply because you remember the equation that was divergence of phi equal minus T mu nu local equilibrium. It becomes global equilibrium now. And then we had nabla mu beta nu plus something involving the current. But at the global equilibrium, nabla mu beta nu is a Killing vector. Therefore, this is 0. So the divergence of this term is 0. The divergence of this term is also 0 because of T mu nu nabla mu beta nu is 0. And the last term as well, because zeta is supposedly constant. So at global equilibrium is a case in which everything is objective. So you don't need to wonder whether you have chosen a proper, say, family of hypersurfaces or foliation, in other words. No, this is everything is objective. Beta is a Killing vector, and you know the general solution in Minkowski spacetime, okay, which is like this. This is the thermal vorticity. This is a time-like vector, which includes the inverse of the temperature. So everything is fine. Now, if you contract this, now let's make this exercise. Let's contract the entropy current with the eigenvector of T mu nu, which defines the Landau frame. So let me show you this. That is, the definition of the Landau frame is such that T mu nu u nu is equal to, well, this is usually called rho or epsilon, right? We call it epsilon or energy density u nu. So it is an eigenvector of u, okay? This is the definition of Landau frame. So this defines what is the forward velocity in the Landau hydrodynamics. Okay, let's multiply this by S by U, and let us check if this relation applies. Then we have S dot UL, then phi dot UL, and then you have this contraction here. So there is a contraction between beta and U, and then you have zeta J dot UL. Now, UL, T mu nu, beta nu, you can decompose beta along U, because they are two time-like vectors, so I can project beta onto U, which is another time-like vector, supposedly, and I have beta dot UL plus an orthogonal, say, vector to U. Okay, this is just the usual decomposition, projection of a vector onto a vector and the orthogonal hyperplane. Now, of course, beta transverse now is orthogonal to, let me see. Okay, so T mu nu this is, yeah. T mu nu, U nu is parallel to U by hypothesis. Therefore, once this contracts with beta is 0, okay? Therefore, you are left with the first one, which is UL T mu nu beta dot UL UL, which tells you that this is equal to, not to beta dot UL, and then this is the Landau energy density, because you have UL T mu nu, okay? So, finally, we have that S dot UL, that we can call the entropy density in the Landau frame, is equal to this scalar product plus rho divided by TL, and then you have minus zeta and L. So it looks like that this is, provided that phi, assume that, well, we don't know that in general, but assume, and you will see this in the exercise of this afternoon, assume that phi is equal to P beta, pressure beta. Then in this case, this would become PL divided by TL, okay? So we will get SL equal PL divided by TL plus rho L divided by TL minus zeta and L. Okay, now let us multiply everything by TL. So we get something which looks like, okay, except we don't know what is zeta T and L, but this is supposed, this perhaps corresponds to a chemical potential, okay, chemical potential TL. So we have a relation which looks like the usual local thermodynamic relation, but there is an however. The reason is that this is possible only if you identify TL with temperature. Some people, or many, I think, believe that out of equilibrium the temperature can be defined, so it's arbitrary in a sense. So there's no way of defining a unique temperature. But we are at global equilibrium. And at global equilibrium, temperature is well defined. Particularly, we have that TL is equal to 1 over beta dot UL, which is for a relativistic relation less than the temperature 1 over square root of beta squared. And you may wonder whether, what is 1 over beta squared? Well, this is the actual temperature at global equilibrium. You can prove that. I can show this example. At global equilibrium with rotation, we have, this beta is a Killian vector, can be written 1 over T naught, 1 omega vector product x. This is a rigid velocity field. It corresponds to a fluid which rotates rigidly along the axis, around a symmetry axis. It's an axis in metric system. And the proper temperature, 1 over square root of beta squared, is equal to T naught squared divided by 1 over minus omega squared R squared. The R is the distance from the axis. This law is called the Tolman's law. Okay? This is the law, corresponds to T square root of G naught naught, corresponds to how the temperature changes in a gravitational field. In this case, it's due to an acceleration. So this is where T naught is the temperature along the axis. So, in other words, if you say stick to the Landau frame, you will encounter a problem if you want to interpret these thermodynamic relations, because you will be forced to admit that the temperature is not the physical temperature in this relation, but it's something else. It's more complicated. Okay? In particular, the temperature of Landau temperature is always less than the actual temperature. And this is quite unpleasant. Now you may wonder is it true that, so maybe U Landau, so maybe UL is simply parallel to beta, and therefore beta itself is a Landau vector. But this is not the case. So this has been shown explicitly. I want to mention that a recent paper of ours. So if you can calculate the mean value of the stress energy tensor with this Killing vector. So you can calculate T mu nu equal trace, and then we have rho global equilibrium T mu nu x. Let's put this normal ordering in order to avoid divergences. If it is a free field, okay, and this is equal to E minus B in general. This is given by this expression as we've seen with B and omega constants, T mu nu. Okay? So you can calculate this with a beta field which corresponds to global equilibrium, and it is determined by these two constants, B and omega. And this is possible, and in general, it has this kind of decomposition. Now maybe, I don't know if you can read these coefficients, perhaps they are too small. Okay, so that is a general decomposition along a basis which is defined by U, so this is the unit vector associated to beta, and then you have more vectors, which are all of them orthogonal to U, alpha, W, and L. This is an antisymmetric combination of the previous three. So this is a basis, except in very special case, well, in singular points. This is a basis of a space-time, and you can decompose the stress energy tensor along this basis with suitable coefficients. What you can then do, you can calculate the projection of T mu nu onto U nu with all these coefficients, and you will find that if you, say, contract T mu nu with U nu, you get rho U mu here, which is the usual term. U here is the, remember, that is the unit vector associated to beta. And then you have plus 3 terms. Okay, this is expected because this is a vector field, G, A, and W, which are coefficients associated to L, to this vector, to alpha, which is, this is proportional to the acceleration, and W, which is proportional to the vorticity to the local vorticity. Now, just to refer to a question of you, is it a heat flux? So in general, these terms are not vanishing. Well, can this be interpreted as a heat flux? Well, I would say no, because that does not imply any dissipation. Although, it is a known longitudinal component of T mu nu U nu. Now, the most interesting question is now. Sorry that I have this. They don't agree with each other, the stick and the microphone, sorry. Now, the interesting question is whether you can find an example where these coefficients are different from 0. And indeed there is. This is a calculation which was, actually, I mean, this was remarked, was pointed out some years ago. But in this calculation, with Matteo Buzzegolo and Andrea Palermo, we calculated the free scalar field, massless scalar field coefficients, so all of them for a free theory. And it is found out that these coefficients vanish, but this coefficient does not. And therefore, T mu nu U nu is equal to, well, the usual p squared over 30 t to the fourth. This is the usual massless scalar field energy density times U mu plus, and then there is something which is also proportional to 3 to the fourth. This is unavoidable because for dimensional reasons, which depends on the xi. Xi is the so-called, so this is a coefficient which defines which kind of stress energy tensor we have. Either for the most common choices are the conformal which is with psi equal 1/6, and the minimal coupling with psi equal 0. So you can take psi equal 0 as the most, I would say, the simplest choice, and then we have something which is different from 0. What it means physically means that UL, so the Landau frame, is different from the Killing frame, okay, for the Killing vector. And so, in other words, it is true that even the massless free scalar case, that TL is not the physical temperature. Yes, please.
So this is then only true in the case when you have rotation and acceleration to get the meaning of
Yes, yes. This is the L involves the local vorticity and local acceleration. Therefore, only in this case you have this difference. But for instance, in the rotating case, they are both different from 0. Okay, this is different from 0. So for this very field here, you can calculate L. This does not vanish. It is a space-like vector. It is a space-like vector whose space component is parallel to the velocity field. Okay, so it is a 4-vector which is space-like, so it's orthogonal to U, but at the same time the space component is parallel to the velocity. So it's a difference. So it's well, of the same order of magnitude, I would say. Okay, let me say this: it's not the same order of magnitude. This is far less because U mu is U mu. Okay, so it's a velocity, but L is quadratic in the thermal vorticity because it is a quadratic combination of W and alpha. Therefore, this is omega of the order of omega squared. So this is a correction of the order of omega squared to the stress energy tensor. But still, yeah, even if it is a say small term, this tells you that UL, so the Landau frame, does not correspond to the Killing vector. And this is this shows you that, you know, that choosing choosing Landau frame may involve some problems at even at global equilibrium. Okay. Yes, please.
So what's the coefficient there at the end? The end is the particles?
Which coefficient, sorry?
There's an end there. So 1 minus
70
70 chi.
psi, yes.
And there's an end in the denominator.
No, this is a pi squared.
Oh, pi squared.
Yes, this is, yes. Sorry, that is, it looks tiny from distance. So yeah, this is a pi squared, yes. No, it's not n, yeah. Okay. I don't have a solution for everything. Okay, just I wanted to point out problems, okay, here. So the first problem I want to point out, the definition of the entropy current depends on the foliation, and the second problem is that Landau frame is not always a good frame. Or maybe, perhaps it's not a good frame at all, I don't know, okay? But the main message I want to convey is that, look, thermodynamics is less trivial than one may expect, okay? So one has to be careful, because some of the statements I have seen in relativistic hydro do depend on thermodynamics, and they are perhaps less general than one may think naively, okay? Good. And now let me go to I would say, to the main course of, of this course, sorry for that, which is one of the, say, most useful, I would say, instances where this quantum statistical approach provides provides to be really indispensable, or at least very useful to obtain a physical result. And this is the calculation of something related to, some calculation of observables, so of something that we can measure in the detector, namely particles, spectra, and spin. it is very useful. Sorry. There is a clear relation between the spectrum and the operators, which is expressed by this equation. So the spectrum is proportional to the trace of, to the expectation value of the quadratic combination of a creation and annihilation operator. Okay. To be specific, I'm using here the so-called covariant commutation relation, namely a commutator between A and A dagger is equal to twice the energy times delta 3 plus P minus P prime. So this is a so-called covariant commutation relation. And this is why you have here this twice the energy. Usually, well, in some physics textbook, in some quantum field theory textbooks, you will find this relation here. Well, in this case, keep in mind that I have twice the energy here to make it covariant. Okay. Now, because this is invariant, and so this is invariant as well. Okay. It is also this approach. Okay, you may calculate this with kinetic theory. So you may have classical approaches, relativistic, but to calculate the spectrum. But in order to calculate the spin, this approach, I would say, is really unavoidable. So there is only one way you can define the spin density matrix of a particle, which is like this in a quantum field theory. So this is the trace, that's the expectation value of a combination A dagger R, AS, where R and S are the spin polarization state, the spin states associated to the composition. Let me write down something. So if you have a field, you may, well, perhaps this is it requires the introduction of more quantities. Okay. So I hope that you are familiar with what this symbol means. So this is the creation of operator of a state which has momentum P and polarization state or spin states R. Okay? So in other words, you can write like A cross A dagger P R applied to the vacuum returns a particle which has a momentum P in the spin state R. Now, if you have the spin density matrix, then you can calculate what is the spin polarization vector by simply making an average, I would say, over these spin states, and there is a specific formula for it. So you have to sum over R, S, D, S, J, I. So these are the matrices representing the angular momentum generators in the spin representation S. Here, to be specific, for instance, D, S, J, I. Let's go to D1/2 Ji. Do you know what these matrices are? Pauli matrices divided by 2, yes. Okay. And then of course you may have D1 Ji equal, well, they have their specific form. And then you can go to any spin S and have they are the so-called generators of the rotation group in the spin S representation. Okay, so it is possible to calculate the spin polarization vector, which is the mean spin vector associated to a particle by making this sum. And mu I p, these are vectors which are orthogonal to P. So let's assume Also, we are in a space-time here. P is a time-like vector. N mu I are three time-like vectors. Well, I will. So of course, this drawing has no meaning except the fact I want to say somehow convey the message that you can choose three space-like vectors which are orthogonal to P. Okay, so these are three space-like vectors orthogonal to P, whose choice is arbitrary. However, there is an important point to be made here, that this choice is related one-to-one to what you mean by spin state here, by these indices. So those indices are one-to-one associated to the choice of these three space-like vectors orthogonal to P, okay? Such that eventually this definition is objective. It means I can choose this as a wish, so I can choose any triplet of vectors orthogonal to P, but once a choice is made, this defines what S and R mean in a way that when you combine N mu I with these indices, you get something which is objective, so it cannot depend on which frame or which set of vectors orthogonal to P you have chosen. Okay. So now we have two definitions which relate, okay? Which relate what? Well, quantum field theory, which included in this the presence of these operators, two observables, spin polarization vector, the spectrum. These are measurable objects. And to what? And to quantum statistical mechanics, because you have a density operator here, okay? And now, if I want to calculate these observables in heavy ion collisions, what I have to do is just to replace rho with the actual density operator with what we believe is the best approximation of it. And I have pointed out several times that we believe that the best approximation of it is the local equilibrium density operator at the time of the local equilibration, so-called, so along this hyperbola, presumably defined by tau naught. And so, I have shown that in the hydrodynamic regime, this can be written down, this can be transformed into the exponential of the sum of two terms, one of the local equilibrium at the present time, and one is the term including the dissipative correction. Now, the local equilibrium time, if I want to calculate a spectrum, now in this case, relativistic heavy ion collisions, there is only one possible choice, and this is the freeze-out hypersurface. The reason being that, well, I want to calculate something regarding the final particles. So these are the quantum operators, okay, related to fields of produced particles, of the final hadrons. And therefore, of course, I have to go, I choose as the hypersurface of final local equilibrium, the freeze-out, okay? This is indeed, by definition, if you wish, freeze-out is the place where local equilibrium ceases to be valid. Ceases means that it is valid up to that point, and then the system is no longer in local thermodynamic equilibrium because we know that it becomes kinetic. So we have the decoupling. Okay? Good. So that is what we have to do. If we want to make a calculation of spectra and spin, we have this operator, and we can, if you wish, neglect this term at the beginning and focus just on local equilibrium, and then perhaps include the dissipation correction in a more evolved or a more correct calculation. So, for instance, we can want to calculate the spectrum which is with the approximation of retaining just the local equilibrium operator. So the local equilibrium, the freeze out. So that means that we neglect this, okay, for the present. And we want to calculate the spectrum. But now the problem comes the following. There is a problem that you can realize quite quickly. So I want to do this at the freeze out, local equilibrium freeze out, and then I have these two operators. So this is, for instance, this would be the expression of the spectrum, or twice the energy, the spectrum of a spin 0 particle. Okay, there is no spin indices here. And then now let me write what we have: p sigma mu t mu nu beta nu minus zeta j mu. Okay, you may add more currents if you wish, divided by zeta, and then we have a dagger p AP. So can we calculate this? Well, as we have seen, this is not an easy calculation, even at local equilibrium. This operator is quite complicated. It's an integral over the hypersurface of freeze out, and well, we don't know. We have seen that if we had here a local operator, this would be easier, because if we have a local operator here, we may think that if beta is lowly varying, we can Taylor expand beta and try to obtain a good approximation. But we don't have a local operator here. So we have a global operator, because this A dagger P AP is not a local operator. This is an operator depending on the momentum. Therefore, it involves the integration of the field over some large region. So what we can do instead, so one would like to do something like this, right? Expand the sigma mu t mu nu beta nu like this in a series in a Taylor series around some point x, and obtain what you have seen last Wednesday. So this term, at the first order in the gradients, the sum of three terms, okay? This is the global equilibrium at point x. This is omega, so the thermal vorticity times the angular momentum, the thermal shear multiplied by this operator q. But in order to do that, it is necessary to have a local operator. And so the way of, so the best way to do that is to turn this A dagger PA into a local operator by using the covariant Wigner operator. That is the covariant Wigner operator. It is well, strictly speaking, is not a local operator in that it involves operator a two-point function. However, it is, after all, an operator which depends on x. Okay. So we have different definitions for the Wigner operator. We have a definition which is suitable for scalar, for Dirac, okay, for fermions, sorry. So they have W, X, K. I don't know if you are familiar with that. This is the norm. This is normally ordered integral of a two-point function of the field, okay, Fourier transformed, and for the Dirac as well. Yes, please. I have a question.
So we are actually doing something from the configuration space into the phase space. So you can
Yeah, I mean, yeah.
the configuration space of momentum in this case to a phase space that is mixing both.
Yes, I mean, that is, what we do is that our task is to find something, to find some formula, okay, to turn this calculation into a calculation where you have the mean value of these objects instead. So let me express, so the goal is the following. I should calculate this, but this has a problem, as I told you, because I mean, here you cannot really expand beta at some point because there is no reference point in a sense. So where is the, so A dagger P, A, P does not contain any X. Okay, that is the, so what our task is to turn this calculation into something like this. Trace okay? And of course, eventually we want to have this, but we have to express this through this expectation value. Because in this case, we will be able to make an expansion of beta like this, okay? And eventually obtain a mean value of the Wigner function, and in turn, which will then in turn provide the mean value of the spectra, for instance. So that is the way we want to and so the general idea is to re-express A dagger A as a function of this operator, okay? And so that is the goal. And how to do that? Well, what we can do is that, first of all, W can be separated into three different terms. First of all, we notice that K is not necessarily on shell, okay? So this is not, in fact, the covariant Wigner function cannot be taken as a, say, straightforward replacement of the distribution function, in that while X, of course, includes space and time, this is fine, K is not in general, an on-shell vector. Okay, from this formula, nothing tells you that this K is on shell. Not even if you replace here, if you plug in here the expansion of the fields. So K is not an on-shell vector. However, you can define three different, so you can split the covariant Wigner function, expectation value, into three, or even the operator, into three parts. The one with positive K squared and positive time component. And we will find the one with positive, oh, this is just algebraic, positive K squared and negative time component, and the one with space-like K squared, okay? And once the field expansion is plugged into the covariant Wigner function, what we find out, and I will show a formula thereafter, yes. What we find out is that this term is associated to particles, to the particle term of the field. This is to the antiparticle. This is called W plus, W minus, and then there is a third contribution, which is the space-like part of what's called the Wigner function, because it requires K squared to be minus K squared to be positive, so K squared to be negative, and this is made of mixings between particles and antiparticles. Okay, now there is some work to be done, and I don't have time to show all the steps in details, but the first thing to do here is to use the field expansions in plane waves to expand W. So, example, the scalar field. For the scalar field, you have this well-known complex scalar field, okay? This is the well-known, for the complex scalar field, well-known expansions in plane wave. Okay, let's put it into the Wigner definition here, so into this formula, and what we get is something like this, okay? So we get, after, this is after taking the average, then we have that Well, if you just really work term by term, you get something which is involve, presence of deltas, and then you have combinations of A dagger A with different momenta, of B dagger B, of the antiparticles, and then you have also mixed terms. Well, and then if you calculate this, if you then apply the splitting, you can easily realize that this term, so that theta k square, so k square positive and k0 positive selects this term here. Okay, this is easy to see because you have this k minus p plus p prime half, which means that k is here is a time-like vector because it's the sum of two time-like vectors. P and p prime are on shell, and also the time component is positive. Whereas here, for instance, you have p and p prime add, and therefore k is a time-like vector, but k naught is negative because you have k plus p plus pi prime. So this term is selected by theta k naught, so theta minus k naught, sorry, so this k naught negative and involves antiparticles. This is k naught positive particles. And finally you have k minus p prime half, which means that k is space-like. Okay? Because p minus p prime being on shell, then you have a space-like vector, okay, if you squared. And you see that this involves mixing of particles and antiparticle terms. Okay? Is it all right? All right? Fine. So as I told you that I cannot go through all steps in detail. However, one key point is the following. You can show that, it is possible to show that k mu, the divergence of k mu de mu of the operator, k mu de mu w is equal to 0. That is a very important point. Because that means that means that d mu, that this is the divergence of k mu w is 0. Whenever you have a field which is at zero divergence, right, that means straightforward consequence is that the integral over some space-like hypersurface, or not even space-like, in this case is independent of sigma. And there is another important consequence, that if you integrate this, you find out that all off-shell contributions to this integral vanish. So k is essentially on shell. Okay? So this is an important point. You can show yourself that k mu de mu wx is equal to 0 just by using these deltas. And also it is important to point out, and didn't mention in the slides, that not just k, this is correct, but also that this applies to all three components. So the plus component, the minus component, to the space-like. So all of these terms are such that k mu divergence of mu, k mu de mu w is 0. Okay. Now, once this is done, then the third step is to show that this relation, so to show that dn over d3p can be obtained by integrating over p naught d sigma mu p mu w plus, in this case, because I'm referring to particles, xp for the spin scalar, for the spin case, and dn over d3p dp naught d sigma mu p mu trace of gamma mu w plus xp, if I'm referring to particles. So these are relations for the spin 0 and spin 1/2 case. Also, this is not easy to, so this is not difficult to obtain. And this is I'm showing you here a derivation in the scalar case. So in the scalar case, maybe we can, shall I go on, or would you like to have a break now? Shall I go 10 minutes break now and then okay. to show this, to prove this relation, okay? So to calculate, I mean, this relation tells you how to calculate the spectrum from the Wigner function for the spin 0 case, okay? And this is the relation, corresponding relation for spin 1.5 particles, which involves the trace of gamma mu W. This is W is, in the case of spin 1.5 particles, I remind you that this is a matrix in the spinor space. So it has 4 times 4 components. This is a 4 times 4 matrix. So in order to get a scalar, I think you have to project it onto the, with a trace onto some component of the Clifford algebra. This is, this tells you that, I mean, you get the spectrum by taking the vector component of the Wigner function. Now, oh, sorry, there is a mistake here. This note should be, that is no P here, too many indices. Yeah, that is the correct relation. Yeah, okay. Okay, let me show, so this one, for the scalar case, so that is the W xk for the complex scalar field, and one can show that k mu de mu W plus minus s, so all of these components have 0 gradients projected onto k. You can probably check this by eye, because if you take a gradient, for instance, take a gradient of mu, this, in this expansion in plane waves, takes down p minus p prime, right? Which is then multiplied by k mu. But k mu is equal to p plus p prime. Therefore, you have a contraction of p plus, so you have, sorry, p prime plus p contracted with p prime minus p, which is m squared minus m squared, which is 0, okay? And similarly for the other terms. So this is quite easy to check, and therefore, from differential geometry, we know that if you integrate this over some hypersurface, provided that you have some boundary conditions fulfilled, and in case of heavy ions, well, I erased that the picture, which is useful. It's always useful, but in the case of heavy ions, that you have no boundary. You know, if you close with the freeze-out hypersurface, therefore this is certainly true. And they have d sigma mu k mu W plus is equal to, we can choose any hypersurface, and for instance, I can choose, for my convenience, flat hypersurface or hyperplane, and so I have d3x k naught W plus xk. So that is, this corresponds to choosing the hyperplane, t equal constant, with n mu, which is 1, 0, 0, 0, and you can check that this then becomes d3x. The space components of the 3 vector and k naught, okay, which is corresponds to energy, although it is not it is not on-shell energy in principle, but once it is integrated in d3x, it will become on-shell. So now you can integrate d3x W plus xk here. So if you integrate d3x, this expression, what you get is that you can see that you have e p minus p prime x. So if you integrate in d3x, what you get is 2 pi cube delta 3 p minus p prime, right? Because you have an integral of one exponential. Therefore, this means that p and p prime coincide, and then one integration in one of these two is trivial. So it means that p equal p prime. If P equal P prime, that means that P plus P prime is equal P, and then you are left with delta K, delta 4 K minus P. So in other words, d sigma dot K, W plus xk becomes twice this factor, 2 pi cube simplifies, and we have d3p over twice the energy. Then we have K naught over twice the energy, delta 4 K minus P, and then we have A dagger PA. Good? Then we can split this delta 4 into delta 3 P minus K and delta K0 minus P0. Now, of course, these two together imply that K is on shell. Because if K is equal to P, right, and P is on shell, then of course K should be on shell as well. Okay? And then, so we have D3P over twice the energy, because now K naught becomes equal to the energy, so this can be simplified. There is another 2, which cancels out. You have D3P over twice the energy, delta 3P minus K, delta K naught minus P naught, or which can also be written as delta K naught minus K squared plus M squared, which is the on-shell condition. And then we have the, again, mean value A dagger PA, P. But now this is a trivial integral. And then we have 1 over twice the energy, delta K naught minus P naught, or again, maybe I should have written this, I will correct that. A dagger K, AK, simply because now we have integration D3P, which sets P equal to K. And then this is equal to K naught minus P naught. So let me, maybe I should correct this now online. Because everything, after all, should depend on K. So I should have written here minus K squared momentum plus M squared, and here as well, right? And now it's, well, now we just integrate over dk naught, this expression, then you are left with dn over d3k. And so we have found the formula that dn over d3k is equal to this expression. Okay, this is what I wanted to show. Good. This is an example of having how to transform the spectrum, which is originally, say, expressed in terms of expectation value of creation and annihilation operator with the Wigner function. And you can do this for the spin 1/2 as well. Maybe this will be shown, I don't know, perhaps we have to agree with in this afternoon's tutor session. Okay, and so what do we do now? Well, we are happy because now, since W is the mean value of local or quasi-local, I would say, operator, then we can use the expansion of rho LE naught around beta x. As I showed, I mean, I have erased it. Yeah, unfortunately, I erased what I need thereafter. And so what we can do, we can, let me write it again. We can take advantage of the hydrodynamic limit and make calculate good approximation of the spectrum at local equilibrium, so e to the minus v sigma mu, t mu nu, beta nu, minus z j mu, w x p or k, we can calculate by expanding in arterial series beta around the point x. And so we have beta x dot p plus 1/2 omega j x plus 1/2 thermal shear q x plus blah, 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 plus higher orders in the derivatives, w xp. So this is what we are going to do. And I remind you that this expansion provides a good approximation only if you are in the hydro limit, so there must be some requirement, namely that gradients of beta should be small, or more specifically, beta over the gradient of beta should be much larger than microscopic interaction length. This is in general interaction length. So, I mean, if the system is kinetic, so it means that it's weakly coupled, then this will become a mean-free path. Otherwise, there's a microscopic interaction length in QCD, for instance, in the near TC. It's not a mean-free path, we know that, because it's not a kinetic system, but it's still, it must exist. You know, there must be some microscopic interaction length, which is, you can find many proxies of it. For instance, eta over S is, in a sense, a proxy of a microscopic interaction length. Now, okay, that's for the spectra. And let's now make a calculation of the spectra, the way that I have sketched here. And so that this is rho LE. So let's check what it comes out. So rho LE is equal to rho local equilibrium freeze out with neglect dissipation. Then we have this mean value. We Taylor expand beta from X, as I pointed out. So we have this expression. Now, so that this becomes a quantum statistical problem, which is well defined, and we have to work it out, okay? So it's not easy to work it out, but it is easy only if you retain the main term. So suppose that the spectra, so that these terms are so small that they can be neglected altogether. So this one and this one, there will be corrections, but let's forget about them. And we retain just the main term here. So we have trace e to the minus beta x dot pz w operator plus. So I have selected the particle part. Well, now we can do that by plugging the w operator. This is already, yeah. Okay, let's imagine that you have removed these triangular brackets here, so we have an operator. So we put the operator in there, and we get this, okay? So we have 2 times 2 pi cubed d3p over twice the energy d3p prime, blah, blah, blah. And then we have the trace e to the minus beta x dot p a dagger p a p prime. So you will say, you make the, okay, you have wasted so the whole morning showing that you want to calculate the mean value of the Wigner function, and then you are back to the calculating the mean value of a dagger p prime, but you must be crazy. No, I mean, I'm not, because I have reduced this calculation to something that I know exactly. That is the difference. This I can calculate. This has been known since the, well, many, many years ago. The 50s, the 40s, the 30s, I don't know. So the trace of E minus B dot Bx, because this is, look at this. It looks like it's local, but it's not. This is beta x multiplied by 4 momenta. So this is the global thermodynamic equilibrium value of A dagger P A P prime. It's not local. This is global, except that you have a 4 temperature, which is the same 4 temperature in the point X that you are interested in. And this is well known. Who knows? Everybody knows that? That is the, well, this is the Bose-Einstein distribution function multiplied by delta. and twice the energy in this case, because I have used the covariant normalization. And you can show that many ways, okay? For instance, you can prove this, well, this is known in thermal field theory, but we can prove this by simply commuting A dagger P and this operator, and then show that you find a formula, and eventually you can calculate this exactly. And therefore, what I have is this 2 divided by 2 pi cubed, and this blah, 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 and this integral, you have this, and you have twice the energy, delta 3, p minus p prime, and the Bose-Einstein distribution function. And okay, now it's easy because you have a delta 3 that p minus p prime, which sets p equal p prime, so this exponential becomes 1. And eventually then you have another delta, and so you get this 1 over epsilon k is the energy, delta k naught minus ek 2 pi cube, and the Bose-Einstein distribution function. And therefore we have, well, at the leading order we have the renowned Cooper-Frye formula. So I have now obtained E dn over d3p equal d sigma dot p 1 divided, so the Bose-Einstein distribution function for the spin 0. Of course, if I do the same calculation for the spin 1/2, I would get the Fermi-Dirac distribution function. Okay? And we are happy in a sense that, well, we have recovered some formula that was inferred or, I don't know, obtained or guessed, I don't know, otherwise. So I don't know. I mean, I have not read this Cooper-Frye paper. Okay, I know that this can be obtained in several frameworks, but we have re-obtained this in this quantum statistical framework. That means that, okay, we are not on a wrong track. Okay, and we can use it to go on, if you wish. Now let me talk about, okay, spectrum is, okay, very important in heavy ion collisions, but as I emphasized at the beginning of this course, there is something that you cannot get otherwise, and this is the spin polarization vector, because this is inherently quantum, so you must start from a quantum statistical framework from the very beginning, because you are dealing with some inherently quantum observable. So first of all, I mean, the chain of arguments is the same. So the first step is to obtain a formula relating the spin density matrix in general, because you may be interested in, for instance, alignment, or you may be interested in something more complicated involving the spin polarization. In the first instance, you are interested in the spin polarization vector, because this is the main, I would say, component of the spin density matrix. The spin polarization vector is also measurable in heavy ion collisions for lambdas and xi's and omegas and hyperons, and also it is quite an important observable. So the first step is to relate, as I told you, that to the spin polarization vector to the Wigner function. This is more elaborate than for the spectrum, for sure, but it can be done. So because, you know, the definition, as you have seen here, is, you know, more complicated. So we have these matrices involved, so it's not that easy, but it can be done. And you can look at, so there is a full stepped derivation in this paper, and you get 3 different formulae. The first one is the most popular, which tells you that the spin polarization vector is related to the axial component of the Wigner function, sorry, to the axial vector component of the Wigner function. But there are 2 equivalent formulae where the first one relates the spin polarization vector to the so-called spin tensor density component of the Wigner function, and this one to the well, I don't know, this is the antisymmetric component of the Wigner function in the Clifford decomposition. So all of them are equivalent. This is more popular. Okay, so now we have a formula which relates, although you have not seen all the steps in the derivation, but you have a formula which relates the polarization vector to the Wigner function. So our task now is to the same, expand the Wigner function around the, so with this kind of decomposition, so this one, okay? So we have to do the same thing here, okay? And now, what is the difference? Well, the difference is remarkable because if we forget about this, so if you remove this and say these are too small, then your result is, guess, 0, right? The result is 0, so you get 0 polarization vector. Only if you go to first order, you will get some non-vanishing result. Well, then you may continue, they go to second order and so on. But of course, this involves gradients of higher order, and you believe, at least it is believed, that they contribute less. Okay? Now, what is you do then, you have to calculate this expectation value. So we cannot stop at the linear order, and you have to go to first order, second order, and so on and so forth. Sorry, to first order in the first approximation. And unlike what was believed, or what I believe, until 2 years ago, 2.5, say, that this term should be included. I thought that because of, you know, I was led by prejudice. The prejudice was that sigma, the prejudice was driven by this Levi-Civita tensor. So I thought that, without checking, that because of this, any contribution from the symmetric shear tensor would vanish. And this eventually turns out to be incorrect. Turned out to be incorrect. So this is not true. So you have to keep this and this at first order in the gradients. So the terms including vorticity and the terms including the thermal shear. Now, how to work this out? The technique, the method, the only method we know to do this is the linear response theory. Maybe I can go to one of the previous lectures. Let me see if I have it not here, maybe in the, so what I mean is, let me see if I, yeah, this one, yeah. Sorry. Yeah, so we have to use linear response theory. So this expansion, you have two terms. So we have e to the minus beta x dot p, which is the main one, and then we have these two, which can be dealt with as small ones, okay, corrections. So you use linear response theory, and this derivation is quite, well, it's not trivial, it's not, say, it's not impossible, but it requires steps and to be done carefully. The full derivation you can find here. This is the most up-to-date derivation of the formula, and what you get is the formula for the spin. Polarization vector, which is two contributions, as I said. One is for thermal vorticity. So from the correlate, this comes from the correlator, the angular momentum vector of the Wigner operator. So from this term here. So the correlator between, then it involves a correlator in the linear response theory between J, X, and W. And there is one coming from the correlator between QX and W. And they are quoted here, and they do not vanish. Okay? This can be obtained differently because it does not vanish at global equilibrium, because thermal vorticity does not vanish at global equilibrium. Okay, so you may have a rotating fluid, in other words, which is a global equilibrium. Therefore, with global equilibrium techniques, you may find such a formula. And in fact, it was obtained earlier with different methods, not with linear response theory, but with other, say, arguments. Whereas this term here, I don't think of any other method than the one that I have just described. Okay? So there is a contribution which is, I would say, here there is a difference in that there is a quadratic combination of momenta here instead of linear. Also phenomenologically this is very important. But numerically it turned out to be as large as this one. Because after all, it is the same order in the gradients. So this is the antisymmetric derivative of temperature. This is the symmetric derivative, sorry, antisymmetric derivative for temperature, symmetric derivative for temperature. Let me, yes, I'm just writing a reminder here.
There is an experimental evidence that the global polarization of lambda decreases by increasing the center of mass energy, going from star to Edison. And this was interpreted as assuming that the phi-pole at LHC is less tilted, so there is a minor somehow vorticity of the fluid. So this is somehow was somehow consistent with the picture that the polarization comes from this vorticity contribution. Now you are saying that there is also this other contribution from the shear, but this I mean should not decrease in principle going from smaller center of mass energy to larger center of mass energy.
Okay.
I imagine that the first contribution is more important when the phi-pole is more tilted.
The answer is that, well, I don't know. What I can tell you is that this contributes to the global polarization. So if you take a relativistic heavy ion collisions and if you integrate overall momenta, then you see something which is non-vanishing. And this is what was shown by, I don't know, somebody showed this plot of the discovery of polarization, that this plot was showing the data as a function of global polarization as a function of square root of S going down as a square root of S. So this is the global polarization. This means that this is S along J integrated overall momenta. So it means that you have to multiply this by the spectrum so integrate the numerator and divide by the total number of particles. Okay? And this gives you a contribution which is non-vanishing along the axis of the angular momentum of the collision. So for instance, vanishes when you go to very central collisions. Okay. This term here does not provide, apparently, so I have not worked this out analytically, but numerically there is enough evidence that this term does not contribute to the integral, to the integrated. So the integral of, say, overall momenta of this term vanishes, essentially. Is there anyone here more up to date than me? So I mean, can anybody confirm what I just said? Okay, no? So as far as I remember, I mean, I have seen a calculation by somebody, I don't remember, showing that this integral, the integral of D3P of this, yeah, okay. Maybe in Los Angeles, it was, somebody showed this, I don't know.
I mean, our looks a little different because we don't have the T hat, but it has a similar form in integrals to 0.
So the overall integral of momenta is 0, right? Yeah, okay, fine. Yeah, so that confirms that that this plot, okay, is just concerned, essentially, the integrated polarization is just driven by thermal vorticity. And, but for the local polarization, the polarization of the function momentum, this is very important. So this is a large contribution. It means that if you, for instance, this is so-called sign puzzle, this is absolutely crucial to fix it. If you forget about it, you will So there have been many attempts in the past to solve, to reproduce the data. And I think, in my knowledge, this is the only say, but after all, I mean, it should be there. I mean, this is really, there is a solid theoretical, I would say, evidence that this term should be there. Okay? So in other words, if you use this kind of formalism, which is in a sense first principle, so based on quantum statistical mechanics, you see that with this term you reproduce exactly the same formula, and therefore this should be there. I mean, so it has not been somehow suggested ad hoc. This is derivation. Okay. Well, I think that I am done. Yeah. So, yeah, there is quarter or 15 minutes of questions, or or just say more coffee break if you if you wish. Oh, there is a question. Yes.
Okay, no, so could you go back on your expression for this last discussion you were having?
Which one? This one?
Yes, please, yes.
Yeah.
So I see you have the t hat is like a time.
Oh yeah, right.
Time-like factor.
Yeah.
Sorry, I don't know the full details of the equation.
Okay.
This term from other research by other people, I see that this is not it's not manifestly covariant.
Yes.
Would that be a problem for you? This not manifestly covariant?
Okay. No, it's not a problem. There is a deep reason for that, so it's not unjustified. In the derivation, okay, the derivation by Yi Yin and collaborators, yes, it has two differences compared. The formula shows two differences. One is the fact that T nu is replaced by local forward velocity, and the other one is that these momenta are projected orthogonal to the forward velocity. So I do not know. I'm not familiar with the formalism they used to derive this, shear-induced polarization. However, in this derivation, I have there is a good reason why this apparently breaks covariance, and the reason is the following: is the definition of Qx and Jx. Okay, these are two say different operators in the sense that, okay, the difference is just a sign. Let me write it extensively. This is the antisymmetric, and this is the symmetric. So as I mentioned, the divergence of this integrand is 0, which makes J mu nu x independent of the hypersurface. So I may calculate this over any hypersurface and get the same operator. Okay? This guy, this integrand, is not divergent 0. Okay? Is twice, so the mu, so the lambda x mu blah 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 is equal to twice t mu nu. So it's not 0. Therefore, this operator depends on the hypersurface. So I cannot calculate this. So it's not a generator of symmetry indeed, and it depends on which hypersurface. So I can calculate on sigma freeze out. What does it mean? In quantum field theory, this means that while Jx mu nu is a tensor operator, means that it transforms under the application of a Lorentz transformation, this transforms as a proper tensor. So this means this is a tensor operator, means that when you talk about tensor, it means that it should fulfill this relation, which leads eventually is shown in the fact that this formula is fully covariant, whereas this object does depend on the hypersurface. So this is not a tensor operator. So if you try to work this out, if you apply lambda and lambda minus 1 to this, you can take advantage of known relation of what happens to T mu if you apply lambda, lambda minus 1. Then what you will get is this is different. So even though this has the appearance of a tensor, once you fix this hypersurface, it is not a tensor operator. Okay? Which means that in the final formula that you will have a dependence, you must have a dependence on this hypersurface at some point. So in other words, if I choose a hypersurface, like the freeze out, then of course, if I had another hypersurface, well, the result would be different. So I must at some point have a dependence on the shape of this hypersurface in my results. Okay? So in other words, this formula is expected to depend on the specific form of the hypersurface. Okay? Now, in general, the specific form of the hypersurface is difficult to model, because, of course, the hypersurface is a geometric object which depends on, it has an infinite number of degrees of freedom. Under some approximation about if this shape is well behaved, in a sense, then what you get is that the only leftover of the dependence of the hypersurface is this vector. What is this vector? This vector is to be taken as the mean normal vector of this hypersurface. Okay? So if I had to choose one vector, just one vector describing this hypersurface, I would take this. This is the normal vector in the middle. It's symmetric. So this, in a sense, is a residual of the dependence of the hypersurface. This T nu is not T nu, so it's not the time vector in any frame. This would really break covariance. This would really say, although this formula is meaningless. This is the time vector in the QGP frame. So in the frame where this hypersurface is symmetric. Okay? When you draw the hypersurface, you draw this symmetric form because you are in the QGP frame, in the center of mass frame. If you went to another frame, like say in a fixed target experiment, this hypersurface in this frame would look like something like this, right? Not symmetric, highly asymmetric, okay? So T nu here is to be interpreted as the mean vector, the mean vector normal to the freeze-out hypersurface in the frame where it is symmetric. Okay? So it's not T nu in any frame. So it does not, this formula does not mean that if you go to another frame, you should keep T nu 1000. No, you should transform this in the other frame, okay, accordingly. Because T nu has an intrinsic meaning in this case. Although, okay, yeah, it does not look, but it's not the first, also another formula that are normally used, that there is vectors which are known, say, local, like U, but I don't know if I answered your question.
Yes.
Mm-hmm. So, well, I think that I have finished, and I would like to finally tell you that if you are interested in this, say, I don't know how to call it, in these topics, please feel free to contact me. And also, if you wish to collaborate, I would be really very happy. And we are open to, say, to interesting new ideas. So here in Florence, maybe Andrea will talk about, we are a group of 4 or 5 people working on these subjects. And if you would like to collaborate or just simply to have an exchange of ideas, please do it. Maybe Andrea can tell you how to contact us. And I hope that you enjoyed it. And well, so I give you 5 minutes more.